this lecture, I will explain what is a DC shunt motor, and DC series motor, and DC compound motor. DC shunt motor. So we have two windings. One is armature winding, and another one is field winding. And the field winding is connected in parallel with the armature. So here I am giving the supply voltage. The current drawn from the supply is line current. The current flowing through the armature is armature current, and the current which is flowing through the shunt field current is ISH. See here, the current drawn from this line is line current. The current flows through armature is armature current, and the current flows through shunt field winding is ISH, and the shunt field winding resistance is RSH. And the same terminal voltage will be same supply voltage will be appeared across this shunt field winding resistance, and ISH is equal to V divided by RSH. If you apply KCL at this node, sum of the currents towards the node is equal to sum of the currents away from the node. IL is incoming current, and IA and ISH are outgoing. So then IL is equal to IA plus ISH. If you go for the armature current, IL minus ISH. Always the current flows from higher potential to lower potential. The back EMF and RA. Back EMF is the EMF which is induced in an armature conductors, and this is a counter EMF, and the armature winding consists of RA. By applying KVL to this loop, so minus V, and current enters into the positive terminal can be read as positive plus IARA, and here plus EB is equal to 0. Then supply voltage V is equal to EB plus IARA, where back EMF is equal to IA minus IARA. In this, IL is line current, and ISH is shunt field current, and IA is the armature current. So coming to this problem, a 230 volts DC shunt motor takes 32 amperes at full load. Find the back EMF on full load if armature resistance is 0.2 ohms and RSH is 115. First of all, draw the diagram of shunt motor. So the supply voltage V is equal to 230 volts. You can remember, if it is a generator, DC shunt generator or any generator, if is mentioned the voltages, that those are the represent the electrical term. That means 220 volts DC shunt generator or 230 volts DC shunt generator means that is terminal voltage. For a DC shunt motor or for a DC motor, input is electrical. That's why this 230 volts is our supply voltage. Takes 32 amperes at full load. Find the back EMF EB is how much if RA is equal to 0.2 ohms and RSH is 115 ohms. And the shunt field resistance is equal to 115 ohms. And the current which is flowing through the shunt field winding is ISH. And the current drawn from the supply is IA. If apply KCL at this node, IL is equal to IA plus ISH. And how we can calculate the ISH is equal to V divided by RSH. V is 230 and RSH is 115. So the shunt field current is 2 amperes. Then IA is equal to IL minus ISH. What is the IL? The IL value is 32 amperes minus 2, that should be equal to 30 amperes. Then back EMF EB is equal to V minus IARA. So supply voltage is 230, armature current we are getting is 30 amperes into armature resistance is 0.2. So 230 minus 6, that should be equal to 224 volts. And coming to the next classification is DC series motor. The field winding and armature winding both are connected in series. This combination is connected in series with the supply voltage. Always the current drawn from the supply is called the line current, and the current flowing through the armature is armature current. Current flows through series field winding is series field current. Now, always the current flows from higher potential to lower potential. If you apply KVL to this slope, minus V plus EB plus IA into RA plus RSC is equal to 0. So EB is equal to V minus IA into RA plus RSC. RA plus RSC. And one more thing, IL is equal to IA is equal to ISC in a series combination. So this is about the series motor. A 4-pole 250 volts DC series motor. So first of all, you should draw the diagram. When an examination, if it comes in an examination, DC series or DC shunt or DC compound motor, first you should draw the diagram. Then you will easily understand. And the current which is drawn from the supply is line current. The current flowing through series field winding is ISC. The series field winding resistance is RSC. The armature resistance is RA. And the back EMF is EB. Back EMF is EB. Okay, so here is given as a wave connected. The wave connected means, okay, number of poles is 4, voltage is 250 volts, A is equal to 2. Wave means number of parallel paths is 2. Flux per pole is 25 into 10 to the power of minus 3. When the motor is drawing 60 amperes, then IL is equal to IA is equal to ISC is equal to 60 amperes. IA is equal to IL is equal to 60 amperes. And the next one is armature resistance. The armature resistance value is 0.15 ohms, and the series field winding resistance is 0.2 ohms. So generally the series field winding is less than the armature resistance, but in this problem is given RA is less and RAC is more. So practically RAC value is less than that of the RA. So here in this case, find out the EB value. First, V minus IA into RA plus RSC. V minus IA into RA plus RSC. So what is V now? 250 minus IA. IA is 60 into RA is 0.15 plus 0.2. So that I am it as 229 volts. After that, EB is equal to 5Zn by 60 into P by A. Why I am substituting means is asking the speed under this condition. So that is 229 is equal to flux is 25 into 10 to the power minus 3. The number of conductors are, I think the number of conductors are 200. So 200 into speed I have to calculate divided by 60 into, and number of poles are 2 and parallel paths are 2 for wave winding. Then I got it as speed is equal to 1374 RPM. And next one is DC compound generator. So DC compound generator. So compound means one more winding is also introduced. This is the armature, and the series field winding is connected in series with the armature, and the current which is flowing through the shunt field winding is RSH. Shunt field winding resistance is RSH. Current is which is flowing through shunt field winding resistance is ISH, and this one is RSC, and the current which is flowing through armature is IA, and the armature winding resistance is RA, and the back EMF is EB. The back EMF is EB, and the supply voltage is V, and the current drawn from the supply is IL. So this is the same diagram only I am drawing here. And if you apply KCL at this node, IL is equal to IA plus ISH, but IA and ISC both are same. If you apply KVL to this first loop, minus V plus EB plus IA into, I have two resistances. One is armature resistance and another one is series field resistance. RA plus RS is equal to 0. EB equal to V minus IA into RA plus RSC. And this is about the long shunt connection, and ISH is equal to V by RSH. Why? Because the same supply voltage will be applied across RSH. This node potential will be V only, and here also same voltage will be applied. Coming to the short shunt connection, the series field winding is connected in series with the supply, and the shunt field winding is connected in parallel with armature. The current drawn from the supply is IL, and the current which is flowing through armature is IA, and this current can be divided as IL can be divided as IA and ISH. ISH is the current flowing through RSH, and here the terminal voltage will be different. The voltage which is appeared across the armature is not V. So in order to find out, you can assume that the voltage potential will be Vx, and using circuit concepts only, you can apply KVL to this loop. The current which is flowing through this one is IL. KVL to this loop. Always the current flows from higher potential to lower potential. Current enters into the positive terminal, can be read as positive. So that is IL into RSC plus Vx. Here current enters the positive terminal, and minus V is equal to 0. Then Vx is equal to V minus IL into RSC. The node potential will be, suppose you can assume that is the A potential. The node potential is Vx, that Vx is equal to V minus IL into RSC. And same, if you apply the KCL to at the node, IL is equal to IA plus ISH, and IA is equal to IL minus ISH, and here IL line current is equal to series field current. If you apply KVL to this loop, minus V plus EB plus IARA plus ISC into RSC is equal to 0. Then the back EMF EB is equal to V minus IARA. So V minus IARA minus IL into RSC. If you want to find out the shunt current, so the potential at this point across this field winding is Vx. So now ISH is equal to Vx divided by RSH. That means V minus IL into RSC divided by RSH. So this is a problem, derivation or formulas of DC compound motor having two types of connections. One is long shunt connection and another one is short shunt connection. And the next one is torque and speed equations. Torque and speed equations. So torque TA armature torque is equal to 0.159 into phi z into IA into P by A. So once design is over, number of poles is constant, number of parallel paths is constant, number of conductors is also constant, 0.159 is also constant. Then the armature torque is directly proportional to flux into IA. Where flux is directly proportional to field current. If you go for the shunt motor, flux is constant. Why? Because the shunt current V by RSH supply voltage is constant, RSH is also constant, and the flux is also constant because the phi is directly proportional to ISH. Then armature torque is directly proportional to IA. As we discussed in the previous session, what is the cumulative compound and differential compound? So coming to the DC series motor, for a series motor, flux is directly proportional to IA. Why flux is directly proportional to IA? Series field winding carries a armature current. So that's why TA is directly proportional to IA into IA. That is armature torque is directly proportional to IA square. And what is meant by cumulative compound? So cumulative compound means the net flux is phi SH plus phi SC. If you go for the differential compound motor or a differential compound, the net value is phi SH minus phi SC. And what is the speed equation? So then speed equation of DC motor, generally the back EMF EB is equal to phi Zn by 60 into P by A. Once design is over, P is constant, A is constant, and Z is constant, 60 is also constant. I can write it as EB is directly proportional to N phi, when N is directly proportional to EB divided by 5, and EB is equal to V minus IA RA divided by 5. For different types of motors, either flux is constant or IA is a variable. So we will see in the characteristics. This is a generalized equation. So for a motor, as we discussed in the previous lectures only, if you want to know the machine's performance, we have to see the efficiency and regulation. And if it is a generator, we should concentrate on voltage regulation. If it is a motor, we should concentrate on speed regulation. Percentage speed regulation is equal to no load speed minus full load speed divided by full load speed into 100. So this is called the speed regulation formula. It is the change in speed from no load to full load, and it is expressed as a percentageal fraction of full load speed. So that is about the speed regulation. So this is very important. Okay guys, we will see in the next video. Thank you.